Let's just jump right into today's explainer. We're going to be unraveling the everyday magic of electricity. You know, that invisible powerhouse force that literally keeps our modern lives running seamlessly. So let's dive right in and see exactly what makes the modern world tick. Here's the roadmap for today. First up, powering our modern world. Then, sources of electrical energy, followed by building an electric circuit. After that, we'll look at conductors versus insulators, and finally, electrical safety and protection.
All right, part one, powering our modern world.
I want you to take just a quick second here and try to actually imagine a world completely without electricity. Think about it. No phone alarm jarring you awake, no fridge keeping your groceries fresh, absolutely no lights once the sun sets. It's pretty wild to think about, right? It's this unavoidable necessity that makes our modern lives not just, comfortable, but literally possible. And honestly, our reliance on electricity goes way, way beyond just keeping the TV or the microwave running at home. We're talking massive scale here. It powers heavy factory machines, the electric trains and metros moving millions of people every single day, crucial medical equipment, and even the space tech and telecommunications networks that keep this entire planet connected. So grasping how this energy actually works, it's absolutely crucial because it is quite literally the driver of human progress.
Moving on to part two, sources of electrical energy.
So to understand all of this, we've got to look at the engine. The electric cell is the most basic source of electricity we interact with. But how does it actually work? Well, it produces electric current through a chemical reaction. It's basically converting stored chemical energy straight into electrical energy. If you look closely at one, you're going to notice a metal cap at the top, that's your positive terminal, and a flat metal disc at the bottom, which is your negative terminal. But, not all cells are created equal. We've got primary cells and secondary cells. Primary cells, like those standard dry cells you pop into a flashlight, well, their chemicals just get used up. Once they're dead, they're dead. You got to replace them. Secondary cells, though, those can be recharged and used all over again. And here's a fun little fact. When you connect two or more of these cells together in a combination, that is literally what we call a battery. Now, beyond the chemical stuff, we also have these incredible alternative sources, like solar cells. These are brilliant little devices that convert solar energy directly into electricity. Now, sure, a single solar cell only generates a tiny bit of power, but when you connect a whole bunch of them together, you get those massive solar panels you see on roofs. They're absolutely amazing, especially for getting electricity out to remote areas where laying down traditional power lines is basically impossible. Okay, part three, building an electric circuit. Now that we've got our energy source, we need to build the road for it. For electricity to actually flow and do work, like making a simple bulb glow, we have to meet a few very specific conditions. The current has to flow from the positive terminal, travel along a completely unbroken path of wire, and connect right back to the negative terminal. So the absolute golden rule here is this. If there is even the tiniest break in that pathway, or say both wires connect to just one terminal, the current stops dead in its tracks and your bulb stays dark. And when engineers are designing these circuits, they obviously aren't drawing tiny, highly detailed pictures of real batteries and bulbs every single time. That would take forever. Instead, they use a universal visual language. A cell is just a long line next to a shorter, thicker line. A battery, just a chain of those cell symbols. A bulb is that little loop sitting inside a semicircle. Once you learn to read these simple line-drawn symbols, you can quickly understand an electric circuit diagram from anywhere in the world. This perfectly illustrates how we actually control that flow of electricity using a switch, or what's sometimes called a key. Look at the left side. That's an open circuit. The switch is off. You can think of it exactly like a raised drawbridge over a river. The physical path is broken, so the current simply cannot cross, right? The bulb stays off. But on the right, we've got a closed circuit. The switch is closed, the drawbridge is lowered, the path is continuous, and boom, the bulb lights right up. Let's head into part 4, conductors versus insulators. So, materials in the electrical world are broadly split into two camps based on how they handle current. First, you have conductors. These are materials that let electricity pass through them super easily. They're basically high-speed, multi-lane highways for current. On the flip side, we have insulators. These are the exact opposite, really bad conductors. They don't let electricity pass through at all. They act just like thick, solid brick walls, stopping the current from flowing where we don't want it to. Let's break down a few common examples. Things like iron, copper, and graphite. fantastic conductors. Things like plastic, glass, rubber, and wood, great insulators. But honestly, here is one of the most surprising facts from the source material. Water actually has a totally dual nature here. Salt water is a very good conductor of electricity, but pure distilled water, that is actually an insulator. It's the impurities and the salts inside the water that are actually carrying the current. How wild is that? So let's look at how these two concepts actually work together in perfect harmony. If you look inside a standard wire, you've got the copper metal, your conductor, acting as that high-speed highway for the current. But covering it is a layer of plastic insulation. Imagine if someone just stripped all that plastic off. Naked wires would expose us directly to the current. By wrapping the conductor inside an insulator, we get to safely transmit all that power right into our devices without the current escaping or, shocking us. Which brings us nicely to our final section, Part 5, Electrical Safety and Protection. I'm sure we have all seen this skull and crossbones sign plastered on electric poles and power stations. It screams, "Keep away," and for a very, very serious reason. As it turns out, the human body is surprisingly a really good conductor of electricity. If you touch a live, high-voltage area, that electricity will eagerly use your body as a superhighway straight to the ground. That causes severe electric shock, nervous disorders, and yes, it can easily be fatal. We have got to treat this kind of power with immense respect. Because things can and do go wrong, we literally build safeguards directly into our circuits. The absolute most important safety device is the fuse. It's incredibly clever. A fuse basically holds a super thin metal wire that melts really easily when it gets heated. So if a circuit short circuits or overloads and starts pulling a dangerously high amount of current, that fuse wire heats up and intentionally melts. By melting, it acts like an automatic switch. It breaks the circuit, stops the flow, and literally saves your expensive appliances from catching fire. It basically sacrifices itself to keep you safe. And of course, we've got the practical, everyday safety rules. Always make sure you're wearing rubber slippers when handling electrical gadgets because, as we just learned, rubber is a fantastic insulator that protects you from grounding out. Always keep your hands entirely dry because moisture dramatically spikes conductivity. Never touch bare wires. And please, whatever you do, never use your home wall sockets for your little DIY experiments. Stick to the small cells for those projects, okay? To wrap up today's explainer, I really want to leave you with this one thought. Electricity has this incredibly dual nature. In a simple light bulb, the filament wire gets so intensely hot from the current that it literally glows, safely lighting up the dark. Yet, that exact same current, if it's allowed to pass through a live wire into a human body, can severely burn and destroy. It is a true masterclass in harnessing the raw power of nature. So, knowing what you know now about circuits, conductors, and insulators, how will you treat the electricity running silently behind your walls differently today? Thanks so much for joining me on this deep dive. Keep learning and stay curious.